All right, in these notes, we are going to talk about chemical reactions, and we know what a chemical reaction is. We know that a chemical reaction involves rearranging atoms. We know that's synonymous with a chemical change. But what we're going to learn this time is that chemical reactions can be represented with chemical equations or can be represented by chemical equations. So what is a chemical equation? Well, a chemical equation is like a sentence that describes a reaction. It needs to be distinguished from a chemical formula like H2O or CO2. A chemical equation has, of course, reactants and products. And we've seen these many times before. The example I'm going to give to begin with here is a reaction in which a substance called ammonia, NH3, reacts with oxygen, O2, to form nitrogen monoxide and water. Now, here we should already know that these are the reactants and these are the products. This is a reaction that happens to occur with all reactants and products in the gas phase. And so I'm going to add what we call state symbols to the chemical equation. And the state symbols tell us what state everything is in. So this is the first new bit of information that I want to include here. What are state symbols? Now, they may or may not be given as subscripts like I've done here, but they are written after the formula of any reactant or product, and they tell you whether it's in the solid state, or the liquid state, or the gas state. So this reaction may not occur, for instance, if it were a liquid, or it may not produce a solid necessarily. Here are some of the state symbols we should be familiar with. S for solid, L for liquid, and G for gas. There's one more we got to add here. Notice that L for liquid is often given as a cursive L and not a lowercase letter L, so it doesn't look like a 1. But finally, we need to include one more state symbol here, and that is AQ for aqueous. And aqueous means dissolved in water. Specifically, we're talking about water as a solvent, and it's very different to have salt, which is solid, salt, which is liquid, or salt, which is dissolved in water. And that's why we need a state symbol for this state, since it's a little bit different than liquid salt or, for instance, solid salt. So that's the first bit of information that we want to consider. Now, before moving on, I want to point out that this is an unbalanced equation. You may have noticed that the number of hydrogens on the left does not match the number of hydrogens on the right. And that does not mean that this equation is wrong. It just means that it is unbalanced. In other words, it doesn't give us the mole ratios that would actually be involved here. So if we aren't already familiar with the concept of adding coefficients in order to balance an equation, then this is a good time to take a break and go over that concept. That's not the emphasis of these notes, but if you're not already familiar with balancing equations, then this is a point to take a break and practice balancing equations. See if you can, if you're familiar with balancing equations, add coefficients to make this a balanced equation. Pause the video here and see if you can add the coefficients. So now that we understand the basics about a chemical equation and what they represent, we're going to learn about 5 different types of reaction. So these notes are really about reaction types. And there's more than one way of classifying reaction types, but the one we're going to learn involves classifying into 5 categories, and we'll go through them one at a time. The first category we're going to learn about are called synthesis reactions. And synthesis reactions essentially are about making more complex compounds from simpler ones. So the first thing we're going to do is write the basic equation for a synthesis reaction, which is A plus B yields AB. And I'm going to elaborate on that a little bit. This is sort of the skeleton or the general form of a synthesis reaction, I want to elaborate by giving a few examples. What would be an example of something like this? This doesn't imply that there's no subscripts or coefficients. For instance, this would be a simple example of a synthesis reaction. Now, hold on a second. I'm not going to add coefficients just yet. I want everybody to spot the fact that this is not balanced the way it's written, but this is how chlorine occurs as a diatomic molecule, so I can't just omit that subscript, and I can't just add one here, but I can add coefficients, and these are the mole ratios that would be involved. And you can see that the basic skeleton, or the general form for a synthesis reaction, is still visible here. Element plus element yields compound. Here's another example of a synthesis reaction. First, I'm writing it unbalanced. Remember, an unbalanced equation is not wrong. It's just not balanced. Now, I've left some space for some coefficients. Can you figure out what the coefficients would need to be here to balance this equation? Now it's a balanced equation. So as you can see here, for a synthesis reaction, we have two or more simple elements or compounds are going to form a more complex compound. So generally, what I'm going to write for a synthesis reaction is that a compound is formed from, and it could be formed from elements like you see above, or from simpler compounds. And I want to give you an example of that second scenario. A compound can be formed from simpler compounds. For instance, you might have heard of photosynthesis. Of course, that's a type of synthesis reaction. So I'm going to give you some more examples here. Photosynthesis is the synthesis of a complex compound, a sugar, from carbon dioxide and water. And while this doesn't seem to match the formula or the general form up above here, it's still considered a synthesis reaction because we're forming a very complex compound from simpler ones. And I could give another example of a slightly more complex synthesis reaction, like the one that occurs between carbon monoxide and hydrogen gas to give methanol. And here we've synthesized a more complex compound. In other words, we've made something more complex from simpler components. But the most common examples we'll look at of synthesis reactions are this type, where you simply have element plus element yields compound. Now, this last equation here is not balanced, but I think it's going to be just a matter of adding one coefficient here to balance it. So that's the first reaction type we're going to examine, called a synthesis reaction. The second reaction type we're going to look at are called decomposition reactions. And just like before, I'm going to write a simple general form for a decomposition reaction. And the general form is AB yields A plus B. So this is essentially backwards synthesis. Decomposition. A compound breaks down into simpler products. The examples I'll give start with the decomposition, for instance, of hydrogen sulfide gas and forming H2 and S2. Again, that's not a balanced equation, but I can balance it with just a few coefficients here. Another example would be silver chloride decomposing into silver and chlorine gas. And here I'm going to add state symbols just because it's a bit more interesting here to show that we really have a solid product forming a solid and a gas. Here the state symbols happen to be all gaseous. Oh, excuse me, that's sulfur will be a solid. So these are examples of decomposition reactions. And of course, just like synthesis could have slightly more complicated examples where a compound is made from simpler compounds. Decomposition can also involve a complex compound breaking down into simpler compounds like this. We'll look at the decomposition of lead 2 nitrate into 3 products: lead 2 oxide, NO2, and O2. So there's an example of decomposition. Even though this isn't going to match that general form perfectly, it's still just one reactant forming several simpler products. So here's how we'll summarize what a decomposition reaction is. It is a compound breaking down, or a compound breaks down into simpler compounds or elements, and into simpler substances would be an even more concise way of explaining that. So that's a decomposition reaction. That's the second of the 5 reaction types we're going to look at. The third type of reaction we're going to classify here are called single displacement, sometimes called single replacement, and we'll write a general form for a single displacement reaction as well. There's going to be 2 versions of this. The first one I'm going to write as AB plus X yields AX plus B. So you can kind of see what happened there. X displaced B. But another version of this that we'll consider is where X displaces A. And you can think of A and B as being the metal and nonmetal, or cation and anion in an ionic compound. And really it's the identity of this element X, whether it's a metal or a nonmetal, which is going to determine which of these 2 scenarios we're looking at. So these are both examples of single displacement reactions. Here's some specific examples. Diatomic chlorine reacting with potassium bromide. I'm going to add the coefficients here as I go to give potassium chloride and displaced bromine. Now you can see here it was the chlorine which kicked out the bromine. So this would be an example of a nonmetal displacing a nonmetal, like in the first example here, or an anion being replaced by a similar element. Another example would be adding magnesium, for instance, to some silver nitrate. And here, I'm going to add coefficients as I go. We will displace silver and form magnesium nitrate. That's also a single displacement reaction where a metal displaces a metal. That would resemble this form of the equation, since the metal which is doing the displacing is going to take the cation's position. So how can we articulate this in a sentence? It's really one element displaces a similar element in a compound. And that is how we'll think of single displacement reactions. One element displaces a similar element in a compound. And you can see the skeleton of, or the general form of the reaction kind of hiding in here in these specific examples. The fourth reaction type we're going to talk about is double displacement. And like the name suggests, it's just like single displacement, only there's going to be not just one element taking another element's place, but 2 elements swapping places. So our general form is going to look like this. AB plus XY yields AY plus XB. So you can see, you could think about it as A and X swapping places, or you could think about it as B and Y swapping places, And these are often ionic compounds, and there may be polyatomic ions involved. Examples would be, for instance, this double displacement reaction, sodium chloride and silver nitrate, yielding sodium nitrate and silver 1 chloride. Now, these double displacement reactions often occur in aqueous solution, so I'm going to add state symbols here, and may involve one insoluble product. And you'll notice that is what we call a precipitation reaction. A precipitation reaction is one that involves the formation of an insoluble product called a precipitate. Very commonly, double displacement reactions are going to have aqueous reactants, but one insoluble product. We call those precipitation reactions because they involve the formation of a precipitate. Here's another example where calcium chloride will react with potassium sulfate, and we're going to leave some room for coefficients again to form calcium sulfate and potassium chloride. Now, we could see that this is not a balanced equation, so I can balance it very simply by putting a 2 here. And we'll learn later how to predict what the state symbols of the products will be, but in this case, calcium sulfate is actually a precipitate. That is an insoluble compound, but everything else I'm going to write AQ for. So the state symbols are a separate discussion that we don't need to go into the details of in these notes. We just want to recognize that these are double displacement reactions. And really, we could write this as two elements swap places. This is the only reaction type of the 5 we're studying where both reactants and both products are compounds, or all reactants and all products are compounds. Compound and compound yields compound and compound. It's likely to be a double displacement reaction. The final reaction type we're going to talk about are called combustion reactions. And we're going to limit our discussion to hydrocarbon combustion. In other words, just the burning of hydrocarbon fuels. There are a few other types of combustion that you may see examples of elsewhere, but in our class, we're going to focus on just hydrocarbon combustion. The general form for this reaction is very different from the others we've been writing, because I'm not going to be discussing it in terms of A, B, X, or Y, but being very specific in that it is oxygen gas that reacts with some fuel to give carbon dioxide and water. And you can reason what elements that fuel must contain. Here's an example of a combustion reaction. The reaction between methane and oxygen gives CO2 and water. Or, for instance, the burning of paper, C6H12O6 and oxygen. When we say burning paper, we mean combustion of paper. When we say burning of methane, we mean combustion of methane. And that means the reaction with oxygen to form these products, carbon dioxide and water. Those are combustion reactions. A couple of notes that we want to include here. First of all, the fuel is a hydrocarbon and oxygen is always a reactant. Without oxygen as the reactant, this would look like a decomposition reaction. And decomposition is not the same thing as combustion. Now, when I say the fuel is a hydrocarbon, that could be something with carbon and hydrogen in it, but it could also include oxygen. So I'm going to write or contains C, H, and O because it doesn't necessarily just contain C and H. As you can see, it could contain O. And you'll notice that this is not balanced. Let's see if we can balance this. First of all, we can balance this one with just those coefficients. And you might notice, interestingly, that that is backwards photosynthesis. In other words, this forward reaction is what happened when plants grow, or the photosynthesis reaction, and this is what happens when plants burn. And here we can balance this pretty simply, I think, if we, well, one carbon, four hydrogens, I can make that happen with just a 2 here. And now I've got 2 oxygens, and 2 oxygens makes 4. So now I've got 4 oxygens on this side. These are examples of combustion reactions. The other note that I wanted to make here is that CO2 and water are always products. And these are exothermic reactions. As you might have guessed, burning things releases heat and light. So those are examples of combustion reactions. They can be a little trickier to balance sometimes, especially if oxygen is in the fuel. But they always have a very predictable format in that we're going to have some fuel reacting with oxygen to give you CO2 and water. And because they're so exothermic, we can reason that the CO2 and water is going to be in a gaseous phase, not a liquid water phase.